Hello, my dear students. I am Dr. Anindita Bhattacharya, Associate Professor in the Department of Chemistry, Christ Church College, Kanpur. Today I'll be taking Solid State Chemistry, which is Unit 4 of BSc second semester chemistry syllabus. So, as we have already studied a part of it in our previous lectures, I'll be focusing on the types of cubic crystals today. We all know that there are four types of cubic crystals. They are simple or primitive type, in which the atoms are only on the sides, whereas in body centered we have cubic crystals in which atoms are based on sides, as well as that yellow one which is in the center of the body. It is just at the center of the unit cell. Next is your face centered cell, in which a cube has 6 faces and all the faces has a atom plus the corners. The yellow one, they are the 6 yellow ones which are showing that they are one on each face, and the red one which are at the corner, they are showing the corner atoms in the unit cell. Similarly, in the last part, the last type is your end face centered crystal, in which there is one each in the end faces. So in this, a cube has 2 end faces and they are 2 yellow balls, which is signifying 2 atoms in 2 faces, plus 8 red atoms are signifying the corner atoms which are there on each corner. Now, if we come to the number of atoms per unit cell in a cubic lattice, a simple cube has, you all know, 8. But entire atom is not given to that particular unit cell. It is being shared by the adjoining cells. So, the number of unit cell is 8 into 1 by 8. Only 1/8 of that atom is being in that particular unit cell, and rest of the fraction is being shared by your adjoining unit cells. And how you can predict, show this? It is like this. See how the sectional cuts are there. The figure shows the sectional cuts. So we have 1/8 of 8 atoms, which is making it only 1 atom per unit cell. Now if we move on to the simple cubic arrangement of polonium, you can see polonium is only having, it's a simple cube, it is having only in the corners, and the space occupied by the atoms in that unit cell is only 52%, and rest 48% goes as a blank space. In the body centered, as I have already told you, that one atom is in the center of the unit cell, and that atom is completely belonging to that particular unit lattice. So in this we have 8 corner cells, which is only 1/8. So 8 into 1/8 is equal to 1, plus 1 that is in the center, that is completely in there for that particular unit cell. So it is 1 plus 1, that is 2. So in body centered, there are 2 atoms in 1 unit cell. So the packing fraction improves. If we now consider the structure of cesium chloride or cesium bromide, they all have better packing fraction, that is from 52% it is increasing to 68%. Then in the face centered, it is again on each face we are having the single atoms, and that is being shared by 2. So we have only half of it for that particular cell. So it is 6 into 1 by 2, that is 3, plus 8 into 1 by 8, that is again 1. So 3 plus 1 makes it 4. So the number of atoms present in face centered cubic lattice is 4. Examples are sodium chloride, sodium Na, then we have potassium bromide, we have magnesium oxide, and here since the packing fraction is much more improved, it covers 74% of the space and we are left only with 26% of the space which is blank. But otherwise 74% of the cubic lattice is completely filled by the atoms. Now if we move on to the end face, again it is a phase thing, and in this we have only 2 atoms on the end faces whereas 8 in the corner position. So it is 8 into 1 by 8, that is 1, plus 2 into half, that is again 1. 1 plus 1 makes it 2. So we have 2 atoms in a end face centered cubic lattice. Now, how we will go for the determination of the radius? For simple cubic cell, it is R is equal to A by 2. A is nothing, that is the side length. Then face centered cubic lattice, it is A by root 8. And body centered, it is root 3A by 4. So, this is how we calculate the radius of the atoms in the cubic lattice. Radius ratio, we have cations and anions both in a particular crystal. So, the radius ratio will always depend on radius of the cation divided by the radius of the anion. So, greater the radius ratio, larger the size of the cation, and hence the coordination number also increases. Now to calculate the density, we have a formula that is Z into Ma divided by Na into A to the power of 3. Z means the number of atoms. Ma is your mass number. Na we all know it is your Avogadro's number, and A, as I have already told you in my previous slide, it is the side length. Now based on this, we can analyze the structure of the lattice. So that is completely based on the radius ratio rule. This table shows that radius ratio and what will be the shape of my crystal. So for example, if the radius ratio is 0.0 to 0.155, then the coordination number is 2. It will be a linear molecule like HF. Then if it ranges from 0.155 to 0.225, then the coordination number is 3 and it is your triangular planar, and the example will be Bn or B2O3. If the radius ratio is ranging from 0.225 to 0.414, then the coordination number is 4 and it will be tetrahedral like your ZNS and SiO4. If it ranges from 0.414 to 0.732, it is the coordination number will be 6. Shape will be octahedral like your NaCl. And the last, if it ranges from 0.732 to 1, it will have the coordination number 8 and the shape will be body centered cubic, and the example is your cesium chloride.